go over my workflow. So I just thought I would quickly go over my workflow when using the Gaussian software package. And hopefully it acts sort of as a little tutorial. And we'll go through each of the input files slowly. And I have a couple of examples with CO and a bigger molecule. So this is going to be sort of start to finish. Like, so how do you build a molecule? How do you run calculations? How do you analyze the results? How do you check that it worked? All of the input files and sort of basic instructions are on my GitHub, gclen/Gaussian files, and then there's the tutorial files subdirectory, which contains all of these instructions, and the example files are in here, sorted into the different cases. So the first thing is, how do you actually build your molecules? I like to use a software package called Avogadro. It's open source, it's free, it's fairly intuitive. So say we want to build CO, there's a little draw tool, and I want to just put a carbon atom there, and I want to take an oxygen atom, and just stick it there. And so now I have my CO. And so if I want to just like save this molecule in a format that I can use, I'm going to save it as an XYZ file, which has the Cartesian coordinates. I can just save it as whatever, co.yz. And so if I look at that file, it just has the coordinates of my carbon and my oxygen, and then there's the XYZ coordinates. So I can put those into an input file for Gaussian calculations, and then I'm going to have some other parameters. And so if you look at the input files in my tutorial files directory, so if I go tutorial files, relaxation examples, CO, there's going to be a bunch of different stuff. So what you're actually going to start off with is an input file and a submission script. And so if we look at the input file, there's a few things. So first, there's some stuff about the resources allocated to the calculation. There's 4 gigabytes of RAM. There's an intermediate or file that gets written out with all the different stuff called the checkpoint file. So I'm going to call it CISA.check. These are large, typically are fairly large binary files, but there's a utility that I'll show you later that can convert it to a smaller ASCII file. And then this is just the number of processors that's being used. Typically, I find 4, 6, 8, somewhere in that range is pretty good. So here we have what's called the route section. So this here's the functional. This is a hybrid functional B3 lib. You can do PBE, PBE. You can do HSC. You can do whatever. There's a huge listing on the Gaussian manual. So if you just Google Gaussian functionals, a huge list and their corresponding keywords will come up. Same thing for the basis set. So here I'm using 321G. You can use larger basis sets, 6-31 plus G star, whatever. And this opt keyword says relax the geometry. So sort of wiggle it around until you get the geometry that corresponds to the lowest energy. Then you have to have a blank line. Then this is just the name of the job. You have another blank line. Here's the charge and multiplicity. So this means it's a neutral atom or neutral molecule, and then multiplicity is 1, which means it's in a singlet state. So if you want to triplet, put a 3. Typically, it'll be 0, 1, or 0, 2. Gaussian will sort of output an error if you have the wrong multiplicity for the number of electrons in your system. And then here, what we saw before is the Cartesian coordinates of each of the atoms. At the end of the file, it requires 2 blank lines. I have no idea why. But as far as I know, it won't work if you don't have the 2 blank lines at the end of the file. So we also have a submission script. And so that is sort of cluster, wherever you're running this, is it's dependent on where you're running it. So this is for a machine called Grex on Westgrid. Here it's just saying the shell to use. The amount, so what actually matters is the amount of wall time. So this is going to be a really quick job. So I'm giving it 5 minutes. But larger jobs, you're going to want to give 24, 48, 96 hours. This is the amount of memory. So I have 4 gigs. I'm saying that I have 4 cores on one node. This just emails me when it starts and finishes, the name of the job. And this is saying load Gaussian and then run Gaussian using this input file and dump the output to a file called output.log. And so the way that I would actually do that in practice is if you go SSH, if I SSH in the machine, and I have the same input file and same output file, I can just submit the job to the queue by using the command qsub and then the submit script. It'll take a little bit to come up on the status screen, but if I do qstat -u and then my username, I can see which jobs I have running. And so these are 2 other jobs, but here it will eventually be eligible, and then once it starts running, it will become active. And specifying that mail flag here says it'll email me on this, at least on Grex, it will email me when it starts running, and it will email me when it finishes. On other clusters, such as Placentia, it just emails you when it finishes, either successfully or crashes or hits the wall or whatever. Just look at that again. So now that we see that it's running, and so it's generating some output files. So you can see that the checkpoint file has been generated. There's an output file. There's some files relating to where the job is running on the cluster. These are sort of less important. It's just a quick job. Okay, so the way that you check that a job has at least terminated normally is if you just look at the end of the output file, and there will be some quote. So I think they're randomly generated, and it will say normal termination of Gaussian at blah blah blah. This was a really quick job. So how do we check that this actually worked? So one way is we can look at the total energy as a function of a SCF step. And so the way that we search for that is we grep SCF done in the output file, and then I'm just going to dump it to a file, say called e.dat. So if I look at e.dat, I have the total energy as a function of step. And so if I use something like newplot, you'll have to do the SSH -y flag to get the X11 forwarding so you can actually see the plot. But if I go plot e.dat using, and then it's column 5, 1, 2, 3, 4, 5, and then say with lines, points. And eventually it will come up, and we're looking for a curve that goes down and then stabilizes. So this is actually not a good example of that, but in larger molecules or longer runs, you'll see a curve that goes down, and then this will stay or like flatline as it satisfies some convergence criteria. So the difference between total energies at SCF steps is less than some threshold. Okay. The other things you want to do, you want to be able to format this checkpoint file. I can't actually look at this binary file. So if I want to put it into something I can read, I'm going to use a utility called form check. So this is part of the Gaussian package. So on Grex, I do this by loading Gaussian. And then I use form check. I do the binary file first, and then I do the formatted file checkpoint file name afterwards. So now I have this fcheck file, and if I look at that, I can see other information. So typically, I don't actually like parse through this file. I just use it like as input for other analysis software, either ones that I've written or ones that other people have written. So you can also see, if you look in the output file, near the bottom, there's a bunch of sort of information. You can see the eigenvalues. So here's HOMO, HOMO -1, LUMO, LUMO +1. These are all in Hartree. I find it's best to convert to EV. But there's a bunch of different pieces of information in here. So something else that we want to do is we want to be able to get the relaxed coordinates. So I find that there's a package called Babel that you can use. So if you go module, load, open, that command only works on Grex. On, say, Placentia, it's something like module load GCC open Babel. But after the module is loaded, then the commands are all the same. So if you go Babel and then the output file, you want to specify your output format, which is XYZ, and then let's call it CO relax XYZ. And so it's grabbed the relaxed coordinates from that, and if I look at the relaxed coordinates, you can see that it shows, the total energy, but that's sort of meaningless right now, and the coordinates in XYZ. Another thing that's useful to visualize is actually visualizing those orbitals, like say HOMO -1 and HOMO and LUMO. The way that we can do that is generating volumetric data files of the wave function. And there's a utility called Cubegem, which uses the formatted checkpoint file as input, and then you can specify molecular orbitals, say HOMO, and it will generate the wave function. We can visualize those in something like VMD. And so the command to do that is you can find on my GitHub or just looking at the documentation. So I'm just going to copy paste it into here. So you have molecular orbital. So I happen to know that the orbital number of HOMO in CO is 7. My formatted checkpoint file is called pizza.fcheck. I'm going to say CO HOMO.cube. And I'm going to generate this file. And so if I look at this file that it generated, the format of this file is saying here's the number of points in X, Y, and Z. Here's the step sizes between the voxels. There's some information about the atoms. And then these are just all the values of psi at each of these points. And so I've already downloaded these onto my local machine. I don't recommend using VMD and sort of these things remotely because it's just very, very slow. So I have the file on my local machine here. So if I use the software package VMD CO HOMO.cube, I can visualize these things. So I'll sort of actually just look at the molecule right now. So I have my C and O and my relaxed geometry. And then if I want to actually view the orbital, I'm going to use the isosurface drawing method. I find doing a solid surface and then just the isosurface. And if you sort of pick some positive value that looks correct, and then do a negative lobe at the same ISO value, but negative, and say you can color it something different. So this way you can visualize the molecular orbitals. And if you do multiple orbitals, say HOMO -1, HOMO, LUMO, all the way up to whatever, make sure you do it at the same ISO value so you can actually have a direct comparison. And then if I want, I can render these into whatever. Okay, so that's sort of the basic of relaxation. So generate the molecule, create the input file. A lot of creating input files is just modifying existing ones, putting in new coordinates, changing the functional, blah, blah, blah. Run the job, check the energy convergence, look around at some of the parameters in the output file, generate the grab the relaxed geometry, and then generate the cube files and visualize the orbitals. So say we want to do something like generating, or we want different basis functions for different atoms. So if you look in the Wolf folder, there's an example input and output file. And so here, there's a couple new things. So here we have the same sort of parameters of resource allocation. I have a different functional here. I have HOC. This gen keyword says that there will be a section at the bottom that says which basis sets to use for each atom. And there happens to be a pseudo potential, so I use the pseudo equals read. The opt we had before, that means just relax the geometry. And here I'm doing it in a solvent. I'm doing it in THF. If you want to do it in benzene, you would replace this with benzene. Before we were doing it in the gas phase, so we didn't need this SCRF thing. Still the same title, charge multiplicity, and then the atom coordinates, and then here I'm saying for the vanadium atom, use this basis set. For everything else, use this other basis set, and here's the pseudo potential. And so the method of this would work in the exact same way. You submit the job, look for the energy, blah, blah, blah. What if we want to do something like TD-DFT to calculate the optical spectra? Some example files here. So here, there are actually 3 input files. So the submission script will be a little calling Gaussian and then running just the one. It'll run 3 separate files, one after the other. So the first thing we do is we take the relaxed geometry and we do a single point calculation. So notice how there's no opt in this route section. It just reads in the stuff, generates the wave function at that geometry, and just outputs it to the checkpoint file. So it's basically the same, exactly the same as we saw before. There's just no optimization. The second input file does some population analysis using HOC. So you just need to specify the basis sets. It's saying read it off of the checkpoint file, read the geometry from the checkpoint file, and do some population analysis stuff. And there's some internal parameters that need to be set just for saying how it outputs certain things. And then the final one is actually the TD-DFT calculation. So it's saying read it in from the checkpoint file, calculate 90 excitations, and then this is just some internal parameter for how it outputs. Additionally, I forgot to put this in, but there's a row CI parameter, which means output the excited state density, which is particularly useful if you're doing if you're looking at electron hole diagrams with multi-wave function, which I might do in a later video. So if we look at the output file, the TD-DFT output file, and I look for excited, I'll get a bunch of these different excited states. So I have, say, the first excited state has some oscillator strength that occurs at this wavelength. Here's the excitation energy. And then here are all the single particle orbitals that contribute. So it's going from an occupied orbital to an unoccupied orbital, and they're all weighted by something. And here are all those single particle transitions. And so there are going to be 90 of these because we specified 90 states. So how do I actually generate the spectra? I like to use something called Gaussian. And so I have an older version of it on a virtual box. but you can get versions for Linux, I think. And so I just have to wait for this to boot up. But it basically just takes in those input files and then generates a Spectra. So here I'm just going to go into Gaussion, and I'm going to open up my TDDFT output file. And if I go to electronic transitions, I can say calculate the UV vis spectrum at, starting at, let's say, 250 nanometers. I'm going to end at 900. And I'm going to use a full width half maximum of 6,000. So these you can sort of play around with. You'll have to see where the transitions are, what full width half maximum looks reasonable. If you have experimental data, sort of kind of match it to that. And so if you click this button here, it will sort of calculate the spectrum. And here, so here are all the excitations we calculated. So you have, S1, S2, S3, and then your spectrum here. So you can do other things. So I find the best way is it generates that plot, but then it also outputs the data to a directory called Gaussion 2.2 in whatever directory you're working in, and it generates these data files, which I find you can plot the data from and make the plots look nice and pretty, and it just has the raw data. But here are all the wavelengths, and here's the absorption at that wavelength, and so you can plot those and sort of customize the plots as you want. So there are other useful analysis packages, say multi-wave function, Gauss view on this virtual machine you can use to sort of quickly look at stuff like vibrational frequencies and eigenvalues and things like that. VMD is particularly useful, especially for visualizing molecular dynamics, if you happen to do that. Yeah, so hopefully this has been at least semi-useful in terms of seeing the general workflow. So you start off by generating the geometry, you do your relaxations and your, you can also relax excited states after you do your ground state relaxations. You can do TDDFT calculations to calculate the optical spectra. You can visualize those in Gaussion. You can visualize isosurfaces in VMD. You can visualize the relaxed geometries in, say, VMD or Avogadro or whatever. But that's sort of the general idea of how I do things, and hopefully this has been useful for whoever is watching.